Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel where we talk about everything that I want to with science and math. And today we're talking about physical science and the classification of matter. This is really chemistry, so you can watch it for chemistry too if you want to. So, classification of matter. So, in this physical science class, if you're doing this as a class, we've done chapters 1 through 14, and they were physics, and now we're going to do the rest. It'll be chemistry, because physical science is an introduction to physics and chemistry, and studies show that people who take it do better in physics and chemistry. So that's why you want to take it, and it's just fun and interesting. So the very first thing we always talk about with physical science, or when we get to the chemistry part, is matter. Now, I teach in public school, and there's a teacher who has a sign in the hall, and it says, "You matter. Unless you're going at the speed of light, then you energy." Okay, it's a science joke, but it's a bad one. It's because E equals mc squared. Matter and energy can actually be interchanged. So you matter unless you're going at the speed of light, then you're energy. Actually, speed of light squared, right? Okay, different ideas that we're going to talk about. One is, I'm trying to look to see if I've got a chemistry book handy. It's in the back of the physical science book. Okay, so a pure substance. A pure substance is only made of one chemical. So it could be pure gold or it could be pure water, but there's only one chemical that makes it up. And if you sample it from the top, the middle, or the bottom, it would be the same thing. Okay, that's our first idea. Now, what do I mean by element? If you look in the back of a lot of science books, probably yours, there is a periodic table of the elements. And these are the things that substances can't be broken down into anymore and them still retain their characteristics. Elements can be broken down into protons, neutrons, and electrons. You've probably heard of those, and subatomic particles, but they no longer have their characteristics. The protons from a gold atom are just like protons from a carbon atom, so there's really no difference there. So the elements are these things that can't be broken down anymore. But water can be broken down more. It can be broken down into hydrogens and oxygens. But once you get to hydrogens and oxygens, they can't be broken down anymore. And those are the elements. And they're in the periodic table, and we'll be talking about them a lot. Okay, the next idea is, let's see. I'm trying to follow along with the book and not hop ahead. Okay, the next idea is going back to that water. What's it called when it is made of elements put together and it's not just one element anymore? It's called a compound. So water is a compound because it's made of hydrogens and oxygens. It's a compound. Another one is carbon dioxide. You're breathing it out right now. And it's a compound. It's made of carbons and oxygens. So if you have different elements put together, you have a compound. Now, you can have the same element bonded together, like oxygen doesn't just hang out just as one oxygen floating along. It hangs out with another one, and it's called an oxygen molecule. So they're the ones that hang out with one just like it. They're still a pure substance because it's still oxygen, but they hang out together in twos. They're called diatomic, and hydrogen does that, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Did I say? I think I said them. Anyway, there's a little group of them, and you'll learn more about it. But anyway, they're called molecules when they're like that. But there's other things in molecules too. But a compound is a substance that's made of more than one type of atom. Now, what is a mixture? Well, first we have to think a little bit more about compounds. Okay, so compounds, our famous compound that we know is water. And water is made out of H2O, everybody knows that, 2 hydrogens for 1 oxygen. Well, hydrogen, when it's just hydrogen hanging out room temperature with other hydrogens, it's diatomic, it's 2 hydrogens bonded together, and it's a gas at room temperature. If you bring fire up to it, it explodes. It's an explosive gas. Oxygen also is diatomic. If it was just hanging out in the room, it'd be a gas floating along, oxygen gas, and it burns. So, very different than water. You put it together in the water and it's brand new. It's a liquid at room temperature. It puts out fire. It doesn't explode or burn. So when you put together a compound, it's totally different than the elements that put it together, that make it up. Now, a different idea in contrast to that are mixtures. Mixtures is where atoms are put together, but they don't form chemical bonds. When you put hydrogen and oxygen together into water, it has chemical bonds that form, and it is a new substance with new properties. If with a mixture, there's no chemical bonds between it, and it retains the properties that make it up. Now, what I like to talk about is one of my favorite mixtures, which is chocolate milk. This is not chocolate milk, that's coffee. But I should have brought chocolate milk to drink instead. Chocolate milk. Okay, so think about chocolate milk. It's a mixture. It's made of milk and Nesquik, or Quick. You got to get the right stuff, nothing else. No Hershey's. It's got to be Nesquik. Okay, now when my husband makes it, he'll get a big glass of milk, and he'll get 1 spoonful of Nesquik and scrape it level on top, pour it in, and stir it up. It's barely brown. It's just beige. When I make it, I get a glass of milk, and I put at least 4 heaping tablespoons. So I put in over a 1/4 cup of Nesquik in mine. Stir it up, and it is a nice chocolate brown. It is wonderful, and I like to stir it up, not too much, so it has a little sludge at the bottom to have at the very end, just chocolate sludge as sort of like the dessert of the chocolate milk. Are they both chocolate milk? Yes. Do they have different proportions? Yes. Mixtures can have different proportions. Also, notice that chocolate milk retains the characteristics of what makes it up. It tastes like milk, it tastes like chocolate, it tastes like sugar. Now, mine and my husband's might taste different, but they still both have the characteristics of everything that made it up. All right? So, you see the difference now in a mixture and a compound. Now, you can have a heterogeneous mixture or a homogeneous or homogeneous. So, what does homo mean? It means same, doesn't it? So something that is homogeneous or homogeneous is the same throughout. It has no layers. So when you buy milk at the grocery store that says homogenized, it doesn't have any layers in it. It's the same white stuff all the way through. But if you go buy milk on a farm, it will have a layer of cream on top. It's not homogenized, and the cream rises to the surface. We have a farm near here that sells milk, and it's interesting. Just very different than what I'm used to getting at the grocery store. So if it has layers, so Italian salad dressing that's, got the layer of like maybe giblety stuff at the bottom, and then it's got the water, the water layer, the vinegar layer, and then it's got the oil layer on top. It's got layers. It is heterogeneous because it is different. It's got different layers in it. So the farm milk is heterogeneous. If it's the same throughout, like Kool-Aid or milk, or my husband's chocolate milk, it is homogeneous. My chocolate milk is heterogeneous because it's got layers. It's got the chocolate milk layer, and then it's got the chocolate sludge layer on the bottom, the delicious part. Yes. All right, so homogeneous, you can remember that, and heterogeneous mixtures. Colloids. Now, what's a colloid? Okay, solutions have particles in them. They're a mixture, but this is one of the things where the parts of science where the terms get changed, sort of what their definition is and how they're really used. It's just how it is. Normally, when you say a solution in chemistry, you are talking about Kool-Aid. That it might have a color, that it's the same throughout, and it's usually clear. It's clear, it can be colored, but it's the same throughout. So like the very best Kool-Aid in the world, black cherry. So imagine everybody's imagining delicious black cherry Kool-Aid, the same throughout, no layers. That's what you think of as a solution. It can be clear and colorless and look like water, or it can have a color to it, but you think of it as clear. If the particles are a little bit bigger, where it's not clear anymore and it's cloudy, but it doesn't settle out, it's usually a colloid. Colloids have bigger globs throughout, but they're evenly dispersed. So milk is a colloid. Milk is cloudy. If you looked at it under the microscope, it'd have little fat globs in it. That's making it not clear, but it's the same throughout. It doesn't settle out. It's a colloid. Another one that the book talks about is glue. Gelatin, like a cloudy kind of gelatin, would be considered a colloid. Now, how you can detect if it is a solution or a colloid, but technically colloid is a kind of solution, but how it's usually used is you can shine a beam of light through it. And if you can see the beam of light, like a sunbeam, like, you ever sat in your house and you think your house is very, very clean, and then it's late afternoon sun, maybe particularly in the winter, and there's this sunbeam coming through your house, and you can see all these dust particles in it that the sunbeam shows up. And you're like, there's a lot of dust in here. Well, that's how you test for whether it's a colloid or not. You take a light and you shine it through the solution, and if it makes a beam of light, then that's called the Tyndall effect, and it's a colloid. So sometimes it's hard to tell, but you can look at some pictures of that to make sure. Now, a suspension is where they get something that's bigger things than a colloid to stay in solution and not settle out by like adding something to it, like bubble tea. Bubble tea has these fibers going through it that holds those bubbles up in it. So it's a suspension. But you can read more about that too. Now, that's classifying matter. Now we're going to talk about properties of matter. The properties of matter can be divided into physical properties and chemical properties. And how do you know the difference is? If it is a physical property, then it is a property of the substance that doesn't have to do with how it reacts with something else. Chemical properties are how things react. Chemicals is always more than one thing reacting together. So physical properties are like color, size, magnetism, state of matter, could be a behavior, but it's something that is just telling about it all by itself. It's not changing to anything else, a different chemical. It is staying the same. So like for water, I could say it's a liquid at room temperature. It's clear, it's colorless. It has a certain density. Those would all be physical properties. Now, the opposite of that is chemical properties, and that tells how something reacts with something else. If I say something's flammable, that would be a chemical property, because for it to flame up, it has to react with something else, usually oxygen, with it burning. So chemical properties is telling its properties of how it reacts with something else. Other physical properties, there's one called ductile, which means it can be drawn into wires, or malleable, which means it can be hammered into sheets. So gold is ductile and malleable. Silver is ductile and malleable. Also, silver can conduct electricity. That would be a physical property. Did you know that? Silver can conduct electricity? It can. We usually don't think of making like wires out of silver because it's too precious, and people would be stealing them, right? Trying to get the silver, even worse than they do with the copper, which is also conducts electricity. Let's see. Now, the book talks about distillation as a way you can use physical properties to separate things. How distillation works is you take a mixture, like say someone's it's the 30s, it's during, or the 20s during Prohibition, and some bootlegger is making some alcohol. So they take corn that's been all mashed up, they let it ferment, and then they want to get just the alcohol out. Well, what they would do is they would heat it up, and then the alcohol has a physical property that it becomes a vapor at a lower temperature than water. So they wanted to separate the corn mash and the water and everything else that was in there with the alcohol that had come from the fermentation. And so they'd heat it up and vapor off, boil off the alcohol. They would send it through copper pipes where it could cool down, because copper is good at conducting heat and electricity as part of its physical properties. It would take the heat away. It would recondense into liquid again, and then they would gather it up. Now, it was pretty dangerous because people would do this just out in the country, out in the woods. And if you're not very careful with it, then it can become impure, and people could die from drinking bad moonshine or have blindness. So that was a danger of drinking this homemade alcohol made in stills. But I've had some relatives that partook in the illegal alcohol business back then. They're dead now, so I guess the revenuers can't get them. But I heard some tales, some interesting tales of people trying to get away from the government people because they had been making illegal alcohol. I don't drink, so I'm not going to participate in making alcohol legal or illegal. But I mean, I drink water, coffee. I don't drink alcohol. There's too much alcoholism in my family for that. People in my family seem to be all or none. No one's social drinkers, either alcoholic or no alcoholic at all. And I don't want to be an alcoholic, so I'm going with no alcohol at all. We don't halfway do it. You know, we're if we're gonna drink alcohol, we go all out and become alcoholics in my family. So no social drinkers here. So chemical properties are how things interact with others, and a chemical change is when something undergoes a chemical reaction and it becomes something different. And what I did in class when I taught this, but I don't have the stuff here, is I lit a match. And I said, okay, this is a chemical reaction. How can you tell? And so the kids said it's giving off, it has fire, it's giving off light, it has smoke, it's giving off heat. The match itself is changing colors. It was tan and now it's turning black. And so we had all these evidence of a chemical change. And the big proof of it is that in the end, I could not get back my wooden stick. It had been changed into something else. It had been changed into carbon dioxide. It had been changed into water vapor. It had been changed into carbon monoxide because it was incomplete combustion. And it had been changed to soot and ash and char. Like coal, kind of blackened wood. So it had undergone a chemical change. It had reacted with the oxygen in the air, and we had had combustion. Now, if you boil water, that's not a chemical change. Yes, it's no longer a liquid, and now it's a vapor, but it's still H2O. One is liquid H2O, and the other one is gas H2O, but it's still H2O. I could freeze it and turn it into ice. It would still be H2O. Those are physical changes, not chemical changes. If you have a chemical change, you have something new at the end. All right, let's see what else we need to talk about. We can use chemical changes to separate things. Weathering could be a chemical change or a physical change. Sometimes rocks can actually react with like acid rain and become something else. Okay, and then our last idea is the idea of conservation. Now, this isn't like reduce, recycle, reuse, which is good, but this is the law, not the suggestion, the law, not the theory, the law of conservation of matter and energy. And this is what it says. Ever since creation, matter and energy cannot be created or destroyed, only changed from one form to another. So like, if I have some atoms here and I put them in a chemical reaction, those atoms are going to come out the other side of the chemical reaction. They're not going to be created or destroyed, just changed from one form to the other. So when I burnt my match, then the atoms were not destroyed. They just got changed. They became water vapor. They became carbon dioxide. They became carbon monoxide vapor. And they became carbon soot. So the atoms were still there, but they had gotten rearranged into something new. You can't create or destroy atoms. And another way to say this is what you put in is what you get out. You can't make Atoms, you can't destroy atoms. They just change from one form to another. And the same thing with energy. You can't make energy. You can't destroy energy. It just changes from one form to another. And then that was the brilliance of Einstein. He figured out that you can change them into each other. And that's equals mc squared, the very famous equation. All right, so you can look, for those of you doing the class, look in the description for the homework. Like, share, subscribe. Science is great, and I'll see you next time.